precision arithmetic, hardware algorithms and analysis. Over to you, Theo.
Okay, thank you very much for the introduction and this kind invitation. Let me share my screen. Can everyone see the slides now?
Yes.
Good. Okay, so the topic of this lecture is mixed precision arithmetic, where the term arithmetic includes really any kind of finite precision computations, but there's a heavy focus here on floating point arithmetic, which is the most widely used and available arithmetic on today's computers. So essentially, a floating point system, it's very similar to scientific notation. A number is represented as a product between the mantissa, which is a small number, and the base to the power some exponent. So that means that a floating point system is essentially characterized by a number of parameters: the base, beta, which is usually 2 today, the precision t, which determines the essentially the number of accurate digits that we can represent a number with, and the exponent range, which tells us how wide the range of numbers are representable in this arithmetic. And all of these parameters are encoded by a finite number of bits, part of which are assigned to the mantissa, so the precision, and part of which are assigned to the exponent, so the range. A fundamental quantity in floating point arithmetic is the unit roundoff, U, which determines the relative accuracy that any number in the representable range of values is approximated with. So essentially, for any number in this interval here, the floating point version of this number is only has a relative accuracy delta, which is bounded by this unit roundoff U. And moreover, we also have this standard assumption, standard model of arithmetic that tells us that every scalar operation, which is in this set here, the fundamental scalar operations satisfy essentially the same assumption. So that the computed operation in floating point arithmetic is the exact operation with relative accuracy delta bounded by the unit runoff. So this is all the general version and theoretical version of floating point arithmetic. In practice, on today's computers, we only have a small number of practical available arithmetics that are supported by hardware. Actually, historically, the two most common arithmetics were the FP64, which is also called double precision, and FP32, which is called single precision, so on 64 and 32 bits, respectively. And there's also quadruple precision on 128 bits, but usually not on hardware, just it is needed in software. And more recently, and probably most importantly as regards this talk, there is now the emergence of lower precisions. So with, in particular, 16 bits or half precision, which are available on new hardware that is driven by the needs of AI applications. So to do a focus on the last three precisions here, and comparing them with single precision here at the top, we essentially are reducing the number of bits from 32 to something that is lower. So FP16 has 16 bits, bfloat 16 has also 16 bits, but the two of them divide these bits differently. So FP16 has a very narrow range. It can only represent numbers in up to 10 to the plus or minus 5 and about 4 accurate digits, whereas bfloat 16 is able to preserve the same range of representable values as single precision, but loses about 1 more accurate digit. So it's a very low number of digits here. And tfloat 32, which is a very bad name because it doesn't have 32 bits, it only has 19 bits, actually tries to get the best of both of these formats. So it has the range of bfloat 16 and the unit roundoff of FP16. So these three formats are available on today's hardware and especially on GPUs, graphical processing units from NVIDIA. And why are we interested in these lower precisions? Well, they bring great benefits. First, of course, the storage, data movement, and communications that go on in a code that uses these lower precisions are much lower because they're proportional to the amount of information we need to move on, which is the number of bits. But also the speed of computations is also faster. Computing in single precision is faster than in double precision, and so on. And traditionally, the speed was proportional to the number of bits. So for example, single precision would be twice faster than double precision. And a notable exception to this fact, which is a bit historical because it's now almost 15 years ago, was the cell processor, where if we look at the speed of these processors and we compare the double and single precision, actually there were different units, but the speed up was ranging between 4x and 14x. So we were getting much better speed ups in single precision. And you might have heard of this processor because it's actually famous for being the processor that was used in the PlayStation 3. But actually, this processor was very interesting also in high performance computing for this reason. And I'm mentioning this historical exception because now the exception is becoming the rule. With this new hardware that I've mentioned that is driven by AI, we now have half precision arithmetic that is much faster than the traditional single precision or double precision. So here you have a table that summarizes the speed, so the floating, what we call the teraflops, which is the number of floating point operations that we can do in a second. So the higher, the better. And you can see that in the recent years, we are getting speedups that are much higher than 2. So for example, on the latest 800 GPUs, the FP16 and bfloat16 are 16 times faster than single precision. Okay, so clearly there is a strong motivation to use these lower precisions in scientific computing. And speed is not the only motivation. There is also the power perspective, because power consumption is really becoming a primary concern in today's supercomputers, which really consume more and more power. Here you have a graph that maybe some of you have already seen that shows the trend of the power that the computers was consuming along the years. The yellow are actually an extrapolation of what would have happened if we continued in this way. So we would be reaching the sun like 5 years ago. So of course we didn't go this way, but this shows that it's important to care about how much power we consume. And the point is that the power consumption is generally proportional to the square of the mantissa bits. So that means that these FP16 and tfloat32 arithmetics consume about 5 times less energy than single precision. And bfloat16 actually consumes 9 times less. So we are talking about order of magnitudes improvement in both speed and energy with these lower precisions. Okay, so these are all the reasons to use these lower precisions. Now let's talk a little bit about the reasons we should be careful about using them, because of course they bring some risks. So I've already mentioned that FP16 has a very narrow range. The precise values are here. So for example, we cannot represent any number larger than 65,000, which is a pretty small number in scientific computing. And so there is a high risk that we are going to underflow or overflow, which means that we are going to have a number that is not representable in this range. And just to give a few examples where this can happen, these are a few pieces of MATLAB code where we're using this FP16 precision. So here I'm just computing the singular value decomposition of a matrix, the SVD function in MATLAB. And you can see that I'm plotting the single or actually double precision variant here, the half precision in the second column, and the relative error in the last column. And you can see that actually for the small singular values here towards the end, the relative error is huge. It's actually larger than 1, which means that what we have computed is not meaningful. Another example where we can run, so in this case, we are running into underflow because the singular values here are really small. They are smaller than the smallest representable number. A case where we have overflow instead, for example, is computing the dot product of 2 vectors with random uniform entries in 0, 1. So this bit of code here. This returns inf as soon as n exceeds about 300,000. So it's a fairly small number in HPC. And actually, we don't even need n to be that large. For example, another example is when we need to do matrix vector products in a chain. So we take A, we compute AX, and then we take the result and we compute A times that, and so on. And if we do that more than 7 times, then we overflow again. And this happens even for very small matrices sizes. And this is actually something that we need to do in neural network backpropagation, which is something that we do in machine learning. A final example where we also have overflow is the LU factorization. I will talk about that a little bit more in the next slides, of a special type of matrix here, a mode 2 round SVD. This is a matrix which has exactly one singular value that is very small and all the others are equal to 1. And in this case, we actually have an overflow as soon as n exceeds 60,000. So this actually was causing some numerical problems in a new benchmark, which is called HPLI. But overflow and underflow are not the only problems that we can get in floating point, in low floating point precisions. For example, here, what we have is accumulation. So consider this example. We are computing a sum of n numbers xi by what we call recursive summation, which is just what you would expect. You sum x1 plus x2 and then x3 and so on until you sum all of n numbers. In floating point arithmetic, each addition is going to generate an error. So for example, x1 plus x2 is going to generate delta 1, which is bounded by the unit roundoff. And then the result, we're going to take this result s2 hat and sum it to x3, and this is going to generate another error and so on. So what I want you to see here is that we're going to have an accumulation of these rounding errors. So what that means is that if we do n additions, we're going to n minus 1 additions, we're going to do n minus 1 errors, delta I, that are going to accumulate. So we can actually prove that the computed sum here is bounded by an error that is proportional to n because of this accumulation. So what that means, well, in general, in single and double precision, we didn't usually worry about this error accumulation because the precision was high enough. But now if we look at these half precisions that I've mentioned, it's actually quite worrying. For example, in FP16, NU is larger than 1 for n larger than 2048, which is a fairly small number. And the picture is even worse for bfloat 16, where the largest n that we can deal with is 256. After that, we have NU that is larger than 1, which means we don't have any guarantee on the precision on the accuracy of what we have computed. I should mention that this is a worst case bound, and in practice, we do not see linear dependence on the errors because of statistical effects in the rounding errors. They don't exactly all accumulate in the same direction. Nevertheless, we actually have proved in previous work that we can expect the error to behave as square root of NU, which is still quite large. So here I'm showing some experiments. So for essentially a large inner product, so a matrix product of size of inner dimension n, and you can see that about 10,000 we are reaching an error of order n with bfloat 16 and FP16. So after that, what we are computing does not mean anything. Okay, so this is a real practical problem. And a final issue that we might have independently of underflow, overflow, or accumulation is ill conditioning. So you might have noticed in the bound that I've shown previously that the computed sum is, the error on the computed sum is bounded not only by n minus 1u, but also by the sum of the absolute values of the summas, and not the absolute value of the sum. And of course, depending on the value of the xi, this quantity here might be much smaller than this one here. And when this happens, we talk about cancellation. This means that the summands have canceled each other, and the result is much smaller than the sum of the absolute values. In fact, what we can say is that the sum is ill conditioned by defining this condition number here, which is the ratio of these two quantities. Just to give you a very simple example, which is not too extreme, but it's really to emphasize that this problem can happen even on easy cases. Okay, here we are summing these numbers here, which are fairly normal, it seems. But because the result is actually 0.1, whereas the sum of the absolute values is about 20 something, we are actually losing about 2 digits because of the ill conditioning. So out of the 3 digits that we can have in bfloat 16, we only have 1 digit of accuracy left because of this. And of course, you can imagine that if I now take examples where the numbers are much larger, if I sum 10 to the power 10 plus 1 minus something, then I will have lost everything. And here we have done only 3 operations. So it's really not a question of errors accumulating. It's just the ill conditioning that kills us. And this is again an example with the summation, but more generally, in scientific computing, we have ill-conditioned problems everywhere. For example, if we have matrices, we can define the condition number of a matrix as the product of the norm of A and the norm of the inverse of A, which in 2-norm is the ratio between the largest and smallest singular values. And if we solve a linear system with this matrix by Gaussian elimination, then we have this classical result here that the computed oscillation is satisfying a relative accuracy that is bounded by a constant that depends on n times the condition number of the matrix times the precision that we've used. So we have in practice matrices that whose condition number is 10 to the power several orders of magnitude. And so that means that these low precisions seem really not usable on these cases. So this is a really high risk as well. Okay, so a little bit of a recap of what I've said so far. Low precisions, they present great opportunities. They have a much higher speed, much lower storage and communications, much better energy efficiency. But they also present significant risks. I've shown a few examples where the stability of the computation is not guaranteed anymore and can actually fail in practical examples. So what people are looking at in the recent years is mixed precision arithmetic, which essentially is the idea that we want to use low precisions to accelerate the computation, but we also want to preserve the stability and accuracy of the result by strategically using high precisions in a few places. Okay, so of course, the question is, what does it mean in a strategic way? And this is very involved work. And I'm going to present a few examples later in this presentation. But first of all, there's 2 different approaches that we can take to mixed precision arithmetic. One is at the hardware level, and I will first present a different list of today's hardware that has already implemented intrinsic mixed precision operations because of this reason. And if we do not have such mixed precision hardware, I will also present an algorithmical approach where we can do this ourselves. Okay, so the first mixed precision hardware that I want to talk about is called tensor cores. So this is a new type of units that has been around for just 4 or 5 years, I think. That was, for example, available on the V100 GPUs from NVIDIA. And they are not really like classical floating point units that we are used to on CPUs. What they do is something different. They are able to compute 4x4 matrix products. So we have 4x4 matrices A and B. We can multiply them together, sum them to another 4x4 matrix C, and that's the result. And they are able to do that very fast because they actually do it in 1 clock cycle. But what's even more interesting is that they are intrinsically mixed precision, because the matrices A and B here, they must be stored in FP16. These units are only valid for FP16 arithmetic here. But the C and D matrices, we have the choice. We can have them also in FP16, but we can also have them in single precision. And so this was for the V100 units. And even more recently, the latest version of these GPUs, the A100, now support also these other arithmetics for A and B, bfloat 16 and tfloat 32. And it's really hard to understand what these units do in practice. There is some documentation by NVIDIA, but it's generally not very clear. And so this calls for new analysis that tries to describe and explain what is going to happen if we use these units. And NVIDIA is not the only hardware vendor doing these mixed precision units. Google has released the tensor processing units, TPUs, that carry MXUs, matrix units, that do essentially a similar operation, but on 256 by 256 matrices, or 128, depending on the model. And here the input is not FP16, but bfloat 16. And this is just an example. And there are other hardware, for example, ARM has CPUs that have similar capabilities, and Intel has announced that they will also release similar units. So we've called all these units, we've tried to essentially unify all these units in a single framework. And we've called it block FMA, where FMA stands for fused, multiply, add, because essentially what these units are doing is, is generalizing the classical FMA units that we have on usual CPUs to block matrices. And so the general framework goes like this. We are assuming we are able to compute this AB plus C, where the sizes of A and B and C are general. The dimension that matters the most is the inner dimension, and we're going to call that little b. And we're also assuming that we have two precisions, a low one, U low, and a high one, U high. And we can have A and B in precision U low, and C and D either in precision U low or U high. So this matches pretty closely what I've described so far. And it's also important to specify how this AB product is computed. And we're going to assume that it's computed in yet another precision that is called U bar, and that the result is then rounded to UFMA, which is either the low or high precision. So essentially, we have a very general model that is trying to include all of the units that I've presented in the previous slides. And the question of the choice of U bar is fundamental, because we're calling this a fused multiply add, but that would only be true if U bar is 0. That is to say, if we can do this product here exactly and then round it, that would be what we call an FMA. But in practice, the hardware that I've described does not implement this choice, because that would be too expensive. And they have considered other choices, for example, taking U bar U low, in which case we don't have any gains in accuracy because we are essentially doing everything in precision U low. This is just a gain in speed, or doing the inner internal computations in precision U high, in which case it's not a true FMA because there are errors in between the computations, but it resembles one because we are doing the computations, the internal computations in high precision, and then rounding the result to possibly lower precision. So essentially, to first order, it looks like an FMA. And so here, again, to drive the point that this framework, which may seem a little bit too complicated, is just, we did it this way to be able to cover all the units that I've presented. So these are the value of the general parameters for the different types of units that I've mentioned. So now the question that we need to ask is, how are we going to use such a unit? Because, as I said, they are not like classical floating point units. They work on matrices, on, for example, 4x4 matrices. So it's not so obvious how to use them. So for example, let's take a fundamental computation, the multiplication of two matrices, A and B. So now two matrices A and B of general sizes, not 4x4. How are we going to do this? Well, it's actually not so difficult. We can simply split the matrices into tiles or blocks of appropriate sizes in order to be able to express this product as essentially a bunch of block FMAs. Okay, so here the inner products are of size B, and so we can use a block FMA. And so this is essentially a block matrix product, a classical one, except that the red parts show what we need to do that is specific to using these mixed precision block FMA units. So we need to convert the input matrices to low precision, and then these products here, we do them using a block FMA. And so now we can analyze this computation to understand what goes on. So for now, assume that the input matrices are already in precision U low. Then if we look at a row of A and a column of B, and we compute the dot product of that, then the classical analysis, I've actually almost shown it before in the case of summation. Here, the only difference is it's an inner product, so we have also the multiplications, but it's going to be essentially the exact inner product where of a perturbed set of inputs. So here, for each term of the inner product, we'll have an error term which translates the accumulation of rounding errors. So here, this theta k is proportional to ku, which for the term number k has been involved in k operations. So we have k errors. Okay. So this is the classical analysis. Now, in our case, it's almost the same, actually. It looks a little bit more complicated, but what we've simply done is we've split the inner product into chunks of size b to be able to use the block FMA. And so this analysis applies to every chunk. So here we have the theta in each chunk, and then we sum all these chunks together. Okay? And of course, error accumulation also goes on into these chunks. So what we get in the end is something very similar. The difference being that the combination of the chunks is done in precision UFMA, whereas the computations intra-chunk, inside the chunks, is done in precision U-bar. Okay, so we have two precisions instead of one. Other than that, there's not much that changes. So this is just, remember, for one row of A and one column of B. So it's for one element of the matrix, but the bound applies essentially for the entire matrix. And so in the end, we have this bound here. And now we need to take into account the initial conversion of the matrices, because remember that to use these block FMAs, we need to have the matrices in low precisions. And so we end up with a bound here, which is the bound that I've just explained, where we have the accumulation of errors plus an extra term which accounts for the initial conversion. Okay, so okay, this is the general analysis. Now we can take a few examples. So in this table, I'm showing the results for different variants. At the two extremes of the table, I have standard matrix multiplication in precision U low and U high. And in between, I have this block FMA. So the first case is where we do the internal computations in precision U low. And this is not very interesting. We only have a reduction by a factor of b, which is due to the way we've done the sum by chunks, which actually reduces a little bit the accumulation, but this is not really the main point. If we do the internal computation in U low, but we still keep rounding to U low every b operations, then we actually don't have a much better bound. So it's not very useful to do the internal computations here, U-bar, in higher precisions. So the most interesting variants are these three here, where we now are using the C and D matrices in the block FMA, so the UFMA, to be the higher precision. And in this case, we're essentially able to negate the accumulation part. Okay, so what we have is a bound that has a constant in front of the lower precision, and then the accumulation happens in the higher precision. Okay. So this means that we are reducing by a potentially very large factor the error bound. So this is the conclusion of this analysis, that we should try to keep the C and D matrices in the block FMA in the higher precision for as long as possible. And this is just an experimental validation of this analysis on the practical unit, the tensor core units that I've described. And so I'm comparing here the error for a classical half precision in black and single precision in blue with the mixed precision variance in the middle. So this is the case where we do the internal FMA in FP16. So as you can see, we have almost no reduction of the error, so it's not very interesting. And this is the case where we do it in single precision. And in this case, we have a very large reduction because we have reduced the constant here in front of U16. And in terms of performance, so here I'm showing the number of floating point operations per second. You can see that having these C and D matrices in the block FMA in single or half precision essentially does not make a difference. Okay, the two variants of tensor cores behave similarly. So this is a very good news. We can get the accuracy boost at no performance cost. And here in the bottom, you have the non-tensor core variants, which are much slower. So yeah, that's the conclusion. The conclusion is that these mixed precision block FMAs can really help the accuracy of the computations by essentially negating, preventing error accumulation to take place. And this is done at almost no performance loss. So one of the risks that I mentioned, the accumulation, we can actually avoid thanks to this special hardware. But of course, now what I want to talk about is what happens if we don't have access to such special hardware. We do have normal CPUs as well that are going to include low precisions. And then we need to find a solution that is hardware independent. So we need to do something from the algorithmic point of view. And actually, there is something that is well known since many decades now. Error accumulation, it's not a fatality. We can fight it. And for example, there is this algorithm that is called compensated summation, which I'm not going to describe in detail, but essentially it does a little trick to compute the errors that we do at each step and re-inject them back into the result to essentially cancel them. And we can prove that the error bound, so this is for summation. And so we can prove that the error bound is reduced from nu to 2u. So essentially we have no accumulation. The catch is that this algorithm is actually 4 times as expensive, because as you can see, at each step of the summation, we're doing 4 scalar operations. So this is not suited for low precisions, because we would be losing most of the gain that we get from switching to low precision. Okay? We could just do the sum in higher precision. It would probably be cheaper and more accurate. So the question that we asked is, how can we preserve the accuracy of the algorithms, but at a much lower performance overhead? Okay, not a factor of 4, not even a factor of 2, but probably like 10% overhead or something like that. And so to do this, we actually used block summation. So I've already mentioned it a little bit. The idea is to separate the sum into chunks. Okay, so we need to compute the sum of n xj. The way we are going to do this is separate the sum in n over b chunks of size b, and compute each of these partial sums si independently, and then combine them into the final sum. Okay, you have a pictorial representation of this algorithm here. This is actually widely used in today's linear algebra libraries. And we can prove that by doing the computations in this way, we only have up to b term errors that accumulate in each partial sums. And then we are combining n over b partial sums. So that's n over b additional errors. So in the end, we have a b plus n over b bound, which is smaller than n. But this is still a bit high because it's still growing linearly with n. So think of b as a constant here, then you have like n over a constant. Optimally, you could take the block size to be square root of n, and then the bound would become 2 times square root of n, which is not linear with n, but it's still pretty high. As I've mentioned, with these low precisions, even square root of n can be quite big. So instead, what we propose to do in a recent paper is to use mixed precision arithmetic to solve this problem. And so essentially, the idea is very simple. The local sums, the partial sums, we're going to do them with a general algorithm that we can call fast sum. And then we're going to combine these partial sums with another algorithm that we can call accurate sum. And as their name indicates, fast sum is supposed to be fast, and accurate sum is supposed to be accurate. Okay. We have a very general analysis, but I just want to illustrate it with 2 simple choices: fast sum in a low precision and accurate sum in a high precision. Right? This is a very natural thing to do. And in this case, what we're going to obtain is essentially a bound that reduces to bu to first order, because this n over b term is going to drop to the second order term. Okay. And of course, the main idea behind this is that we're only doing n over b additions with the accurate algorithm. So that's a small fraction of the total number of operations that we're doing in an expensive way. Okay. Out of n operations, we're doing n over b. So for example, if b is 100, we only are asking for a 1% performance overhead. Okay. So this is very small, and we still have a bound that is constant and does not grow with n. So just to illustrate this numerically, here you have the comparison between standard summation and this fab sum, so fast and accurate block summation in single and half precision. So this is the error that I'm showing. You can see that for the standard summation, we do have the error that grows with n and actually quickly reaches 1 in half precision, whereas FABSUM maintains a constant error. So we are happy about this. Okay, so far I've focused a lot on the accumulation side of things, which can be a problem. But another potentially important issue is the solution of ill-conditioned problems. For example, in the context of linear systems. So in this case, I want to talk about iterative refinement. So the standard method to solve a linear system AX equal B is to compute the LU factorization of a matrix A, where L and U are triangular matrices, lower and upper, which then allows us to solve this system by two triangular systems, which we know to solve easily. And what has been proposed many decades ago already is to use an iterative procedure, which consists in first solving, computing a first initial solution as above, but then refining the quality of the solution via an iterative procedure, where we essentially compute the residual here and then solve for a correction term di, okay, where we need to solve this linear system here and update the solution with this correction term. So this is essentially Newton's method applied to the solution of linear systems. And if we were able to solve the correction term here exactly, we would actually converge in one step. But of course, then we would know how to solve linear systems exactly. So that's not what we do in practice. We use the LU factors computed initially. So that's why it takes a few iterations to converge. And the precise precisions that are used at each step make this a very versatile algorithm. There has been many precisions, many variants that have been proposed. And actually the Carson and Hyam 2 years ago have analyzed the most general version where we can parameterize every step by a different precision. UF for the factorization, UR for the residual, U, which is the working precision. So everything is stored in precision U and it's our target. And a general solver for the correction equation here, which satisfies a relative error phi I, which can be anything. And they have this theorem that says that if phi I is less than 1, then we will converge and we will get an error that satisfies this forward error here. Okay. So which solver we use for the correction equation here? There's a number of solvers. One solver is LU. And this is what has been used in practice for many years. But this is the problem is that it's restricted to well-conditioned matrices because the condition for convergence is the following one here. So this, for low precisions, we can only deal with small condition numbers. And to tackle more ill-conditioned matrices, a different solver has been proposed. I'm not going to detail it because it can get technical, but essentially we use an iterative method, the generalized minimal residual method. And this allows us to tackle much more ill-conditioned matrices. So I just wanted to give an overview of all these variants. So essentially, this is the general version that I've presented. So then, the first traditional variant was, from the 50s, essentially. And where the residual was computed in quad, but then everything was done in double precision. And then the fixed variant was proposed later and essentially was just seen as a way to stabilize a possibly unstable initial factorization. But the more interesting version today with low precisions is this one, where we do a low precision factorization. So here in this example, we do a single precision factorization, and we're still able to get a double precision accuracy. But the catch is that we need to have the condition number that is small enough. Okay. And then I mentioned that the most general version was from Carson Hyam very recently, where we can have possibly three different precisions. And as I mentioned, depending on the solver, if we used LU, then we are restricted in the condition number. But if we use GEMRES, then we can get much more ill-conditioned matrices. And this is for a single precision factorization. But actually, now that we have half precision, we have many new variants that become possible. And here, these new variants become important because otherwise we are restricted to condition numbers that are very small. Okay, and I just wanted to show this figure here, which is from a paper that was using the cell processor, which was using, as you remember, the PS3 processor. So here I just wanted to show that already back then they were getting, so this is iterative refinement here in green, and the double precision factorization is here in the bottom. So they were already getting very large speedups on this hardware. So let me skip this part because I want to leave time for the questions. I wanted to essentially do a comparison between these historical processors and what we have today with tensor cores. So here, as you can see, the double, this is on the GPUs on the tensor cores. This is the double precision variant here, and the half precision is much faster than just a simple factor of 2 or 4. And okay, and so here you have a matrix. So this figure shows the performance. Sorry, this is an easy matrix because the number here shows the number of iterations to converge. But I also wanted to show what happens when we get a more difficult matrix. And in this case, this is the half precision factorization. And it does not converge anymore because the matrix essentially is more difficult. And this is what we get with tensor cores. So the dark blue is just normal half precision. The light blue is half precision with tensor cores. So you can see that the accuracy boost that we get from tensor cores is critical. Okay, so conclusions. We have really a lot of reasons to want to use these low precisions, many opportunities in terms of speed, energy, storage, and many other things. But as you saw, I gave a few examples where we are actually putting at significant risk the accuracy of what we are computing. So mixed precision arithmetic has emerged in the recent years as probably one of the most promising and successful ways of dealing with these risks. And the good news is that more and more hardware are realizing that and introducing mixed precision capabilities internally, intrinsically. But and that makes them also more complicated. That's the downside. So it's crucial to to understand them and to do a lot of analysis to know how to exploit them effectively. And in the case where we do not have such special hardware, we can also save the day with special algorithms that are doing special tricks by mixing these different precisions. So my slides are available at the URL that you can see here. And I would be happy to take any questions now.
Thank you, Theo. That was a wonderful talk. Could I ask everyone to turn on your microphones just for 5 seconds and then give Theo a live round of applause, please? Right, and if you could turn them off again now, just to avoid